Hello, everyone. My name is Rustam Sadykov. I will be talking on minimizing critical points of functions on closed manifolds. This is a joint work with Stanislav Trunov. Stanislav Trunov is my student. He is doing his PhD at Kansas State University. So I will be talking about minimizing critical points of smooth functions on a closed manifold M. So M will be a closed manifold and F will be a smooth function on the manifold M. A point X on the manifold M is said to be critical if the differential of the function F at this point is 0. To visualize critical points, we may assume that the manifold M is embedded into the Euclidean space Rn. In fact, we may embed the manifold M into the Euclidean space in such a way that the function f is the height function. In other words, we may assume that the function f on the manifold M is given by the projection to the last xn axis. Then in this case, a point x on the manifold M is critical if and only if the tangent plane at the point x is horizontal. Here on this picture, the manifold M is embedded into R3. So here you can see a two-dimensional surface that is embedded into R3, and the function is given by the projection onto the last axis, so that the function f is the height function. There are 6 critical points over here. These are precisely the points at which the tangent plane to the manifold is horizontal. Today I will discuss a classical problem which asks to find the minimal number of critical points of functions on a given closed manifold M. So here, the manifold M is closed, and we are looking for an efficient function which has the minimal number of critical points possible. Such a minimal number is denoted by crit of M. For example, the minimal number of critical points on the two-dimensional sphere is 2. For example, we can embed the sphere S2 into the three-dimensional Euclidean space and consider the height function. The height function in this case has only 2 critical points, namely the minimum and the maximum. There is no function with only 1 critical point on the sphere S2. It might be slightly more difficult to determine that the minimal number of critical points on the torus is 3. Of course, if we just take a standard embedding of the torus into R3, then the minimal number of generic critical points will be 4. However, it is possible to embed the torus in a different way, in slightly more complicated way, so that the number of critical points is 3. In this case, we would have 1 minimum, 1 maximum, and we may arrange that the third critical point is a monkey saddle. In fact, for any orientable surface closed of dimension 2, the number of critical points can be always 3. We can always find a function on such a surface so that it has only 3 critical points. So if I go back to this example, you can see that here we have a surface with 2 handles, which implies that any Morse function on such a surface has 6 critical points, because we would need 2 critical points for a minimum and for a maximum, and for each handle we would also need 2 critical points. So if a surface has G handles, then a function would have 2G plus 2 critical points, under the assumption that the function is a Morse function. However, if we do not restrict ourselves to considering only Morse functions, then we would be able to find a function with only 3 critical points, one minima, one maxima, and one critical point in the middle, which would be a very complicated singular point. Of course, in the case of two-dimensional surfaces, one can find these functions by hand, and one can prove by hand that these are optimal functions, that it is not possible to find a function with less number of critical points. However, in general, for higher dimensional manifolds, the question of finding the minimal number of critical points is a hard problem, and you may, for example, try to do it by hand for RPN, and you will see that this is not so easy. In the case of RPN, the question has been answered. The answer is n+1. For example, for RP2, one can find a function with only 3 critical points. In general, for RPN, the answer is n+1, but it requires already some theory to prove such a result. As I said, this problem is classical. It is the problem of finding the minimal number of critical points of functions on a given closed manifold. This is a very old problem, and one of the tools that is used to solve this problem is called the Lusternik-Schnirelmann category. Lusternik and Schnirelmann worked on related problems like 90 years ago in 1930s. And in particular, they introduced Lusternik-Schnirelmann category. The Lusternik-Schnirelmann category gives the lower estimate for the minimal number of critical points of functions on a given manifold M. Next, I will give the definition of this category, this number that gives us the lower bound for the number of critical points. The Lusternik-Schnirelmann category of a manifold M is the minimal number of open sets U1 through UN covering the manifold M, and such that each of the sets UI is constructible in the manifold M. Here, I do not require that these sets U1 through UN are constructible. These sets might be very complicated. They may have complicated homology groups. They may have non-trivial homotopy groups. However, I require that these sets are constructible in M. In other words, each of these sets can be deformed to a point on the manifold M. Using the Lusternik-Schnirelmann category, one can, for example, show that the minimal number of critical points on RPN is n+1, and of course, one can construct by hand a function with precisely n+1 critical points on RPN. The reason why Lusternik-Schnirelmann category is helpful for studying the minimal number of critical points on a manifold is because this invariant is a homotopy invariant. And in particular, one can use methods of homotopy theory to calculate the category of M. However, this invariant is not so easy to compute, and still for many manifolds, this invariant is not known. With Stanislav Trunov, we introduced a new notion, which we call ball filling, and we defined a new invariant, which we call B cat M. This is the minimal number of compact balls U1 through UN in the manifold M, such that these balls cover the manifold M and such that their interiors are disjoint. So we are looking for the minimal number of such compact balls. The difference between our definition, and the definition of the Lusternik-Schnirelmann, is that in the definition of Lusternik and Schnirelmann, the sets U1 through UN could be arbitrary, maybe non-contractible sets that are contractible in the manifold M. We consider compact balls. So in our case, each of these U1 through UN is a ball. In particular, these balls are contractible, and they're contractible in M. On the other hand, we require that the interiors of balls are empty. With Stanislav Trunov, we proved that B cut of M, this invariant, is precisely the same as the minimal number of critical points on the manifold M. This theorem somewhat clarifies the original Lusternik-Schnirelmann estimate. Also, this theorem has been known at least in the case of manifolds of dimension 3. In 1969, Takens proved a result which is very similar to this one for manifolds of dimension 3. And in fact, apparently, Takens considered this problem for manifolds of high dimension. And he explicitly formulated an open problem, which is one of the steps in proving this result. So the reason why I say that this result somewhat clarifies the statement of the Lusternik-Schnirelmann theorem is because it is easy to notice that every ball filling defines a categorical covering. This is because in the ball filling, we consider covering by balls, and these balls are contractible in the manifold M. And so because of that, given a ball covering of the manifold M, it is easy to construct a categorical covering of the manifold M. This clearly implies that the invariant B cut of M is bounded below by the invariant cut of M. On the other hand, by the theorem with Stanislav Trunov, we know that B cut of M is precisely the same as the number of critical points on the manifold M. This equality, followed by the obvious inequality, gives us precisely the inequality of the Lusternik-Schnirelmann theorem. So next, I would like to apply these ideas to find the minimal number of critical points of functions on four-dimensional manifolds. To do this, I will need the definition of homology Heegard decompositions. To begin with, one handle body of dimension 3 is a three-dimensional ball with one handles attached in an orientable way. So here you can see that we start with a three-dimensional ball and we attach one handles. One handles means that this is just a segment times two-dimensional disk. So we attach this one handles, and when we attach one handles, there are two ways to attach a one handle. It can be attached in an orientable way, so that the resulting manifold is orientable, and it is also possible to attach it in an non-orientable way, so that the resulting manifold is non-orientable. We consider only those one handle bodies where each handle is attached in an orientable way, so that the resulting manifold is an orientable manifold. You can see also that the homotopy type of a one handle body is just a wedge of circles. Now, a homology one handle body is a compact connected oriented three-dimensional manifold with connected boundary and with homology of a one handle body. So I do not require that this three-dimensional manifold has only handles of index 0 and of index 1. This handle body may have handles of index 2. However, what is important is that its homology are precisely the same as the homology of the wedge of circles. Homology one-handle bodies appear very naturally in three-dimensional topology. For example, suppose that K is a knot in S3. Let N of K be an open tubular neighborhood of K. So this is, so to say, an open thickening of the knot K. Then the complement of this open thickening of K is a homology one-handle body. This may not be actually a one-handle body, but it is a homology one-handle body. Of course, when K is a non-knot, then N of K is a standard open torus in R3 and S3. And of course, its complement is also going to be a solid torus. However, if K is knotted, then the complement to this solid, to this open torus N of K may not be a torus. But we could say still that it is a homology one-handle body. A homology Heegard decomposition of a closed-oriented three-dimensional manifold is a decomposition of the manifold M into two pieces, x1 and x2. These two pieces are required to be homology one-handle bodies. Their interiors should be disjoint, and they should intersect only over their boundaries. So the intersection x1 and x2 is the same as the boundary of x1, and it is the same as the boundary of x2. Here's a sketch of such a decomposition. So we have a manifold M, and we decompose the manifold M into two parts, x1 and x2. X1 and x2 are compact manifolds with boundary which is the same. So the boundary of x1 is the same as the boundary of x2. When the compact manifold x1 and x2 are genuine one-handle bodies, not homology one-handle bodies, but genuine one-handle bodies, in this case, the homology Heegard decomposition is actually the standard Heegard decomposition. So this is a Heegard decomposition of a three-dimensional manifold. But now we consider more general Heegard decompositions, which we call homology Heegard decomposition. In homology Heegard decomposition, we allow these manifolds x1 and x2 to be homology one-handle bodies, not necessarily one-handle bodies. For example, if we go back with an example that we considered just a couple of minutes ago, we can take here a knot, or maybe even some one-handle body inside of S3, then the complement of a one-handle body is going to be a homology one-handle body. And this would give us a homology Heegard decomposition of S3 for any embedding into S3 of one-handle body. This decomposition of the sphere S3 may not be a genuine Heegard decomposition because, as I mentioned before, the complement in S3 to a one-handle body is not necessarily a one-handle body. The complement might be a homology one-handle body. However, still this composition is good enough for our purposes, and we would like to consider them. Recently, in four-dimensional manifolds, there appeared a new technique which is called trisections. Trisections turned out to be a very powerful tool for studying four-dimensional manifolds. So let M be an orientable closed connected four-dimensional manifold. I will define at the same time a genuine trisection and a homology trisection. In both cases, if a trisection or homology trisection is of genus G, it means that we have a decomposition of the manifold M into three four-dimensional pieces, x1, x2, and x3. These pieces, x1, x2, and x3, are four-dimensional one-handle bodies of genus G. So each of these x1, x2, and x3 are obtained by attaching one handles to a zero handle, which is a four-dimensional ball. Furthermore, when we take the boundary of any of these one-handle bodies, we require that this the boundary of the one-handle body is decomposed into two pieces, x I minus 1I and x I plus 1I. These pieces are precisely the intersection of xi with the other two one-handle bodies. Furthermore, the decomposition of the boundary of xi in the case of genuine trisection should be a genuine Hilbert splitting. In the case of the homology trisection, this decomposition of dxi should be a homology Hilbert splitting. So I would like to point your attention to the fact that both in the definition of a trisection and in the definition of a homology trisection, the manifold M is decomposed into genuine one-handle bodies. So the manifold x1, x2, and x3 in both cases are genuine one-handle bodies of genus G. However, trisections and homology trisections differ in that when we take the boundary of xi, we get a decomposition, a splitting, and in one case, the splitting is a Hilbert splitting, and in another case, in the case of a homology trisection, we have a homology Hilbert splitting. It is known that every four-dimensional manifold admits a trisection, and in particular, every four-dimensional manifold, oriented, closed, compact, connected four-dimensional manifold admits a homology trisection. Trisections were introduced by Gay Kirby, but here I draw a picture from a somewhat simplified trisection of four-dimensional manifolds, which was introduced by Baikur and Sadykov. So to construct a simplified trisection, one takes the manifold M and map it to R2. So here we consider a map from M to R2. Then such a map can be simplified so that its singular set is very nice. So it has this red curve of singular points of index 0, and there are blue curves of index 1. So here there might be many curves. So here kind of maybe you can see it clearer this way. So there might be many curves of index 1, and the inner circles, they have 3 cusps each, and there are no other singularities. What one can do is one can cut R2 into 3 pieces. So this is one piece, this is another piece, and this is the third piece. And then one can take the inverse images of these 3 pieces. And the inverse images are F inverse of x1, F inverse of x. So the inverse image of this piece is going to be x1, the inverse image of this piece is going to be x2, and the inverse image of this part is x3. So that this part on the plane is actually the image of x1, this part on the plane is the image of x2, and this part on the plane is the image of x3 under the map F. This is a nice way to visualize trisections, and this is a nice way to prove that every closed-oriented four-dimensional manifold admits a trisection. So the relation of trisections and homology trisections to the original problem that I was discussed is clarified by the following corollary. So a closed, simply connected, oriented, manifold M of dimension 4 admits a function with 3 critical points if and only if it admits a homology trisection of genus 0. So for 4-dimensional manifolds, in general, if you have a 4-dimensional manifold, then you may need at least 5 critical points. I mean that the minimal number of critical points of functions on a generic 4-dimensional manifold is 5. If a manifold is simply connected, then of course one would expect that the minimal number of critical points of a function should be less than 5. And at this moment, we can prove that the number of minimal points of a function of functions on any simply connected manifold is 3 if and only if this manifold admits a homology trisection of genus Z. So a homology trisection of genus Z means that basically the manifold can be decomposed into the union of 3 poles. And this decomposition should be nice. It should satisfy the conditions that I have formulated before. So this is all for my talk. So the 2 results that I wanted to present today are the result about the non-U invariant BCAT. So we have shown with Stanislav Trunov the invariant BCAT of M is precisely the minimal number of critical points of functions on a given manifold. And second, with Stanislav Trunov, we proved that a simply connected oriented closed manifold of dimension 4 admits a function with 3 critical points if and only if this manifold admits a homology trisection of genus 0. Thank you.